All right, how's it going? So one thing we didn't get to yesterday with SED, one of the instructions that you needed for those exercises is W. That's a write instruction. So you can do something like SED, and we could search for a pattern like fruit. And say if we match that pattern, we want to write to file 1. And it will read the input file, and in this case without -n it'll copy to output, but anytime that an input record matches this regular expression, it will write that record to this file. And these writes are appended, so you'll get multiple copies in there. So so here's our foods. Yeah?
Is there any way we can do that when it reaches the second fruit or the third fruit?
Oh, let's see. Not directly, but you could pipe that file into, I mean, not directly. Not that I know of. There's probably a way, but.
How do you break the files into pieces?
So I would either send it to standard out and run that through another thing like head or another sed command, or put it into a file and then post-process the file with another sed command. There's probably a fancy way to do it in one line, but I don't know what it is. So if we do this, right, it copies all of our input to standard out, which we may or may not care about, but it also creates this file 1 with the records that matched our fruit. So typically if you were doing this, you'd throw in a -n, and then it still does that output. So you can search for something else. So you could put multiple commands into a program file. So here we're searching for any of these 3 types, and we're writing 3 different files accordingly. So let's do -f type foods, and now we've got 3 files. So that's the missing instruction that you needed for question 5, where you were trying to split a file into 2 pieces. But barring that, so how many people thought about these exercises?
I got about 4 or 6, I think.
Okay. So remove all lines beginning with today. How can we go about that?
Just print any line that's not a day in the beginning.
Okay.
Using said caret today.
So we've got a few options. So remove all lines beginning with today. So we could say if it's not this, we should print. Right, and probably do a -n. Or you could do sed, look for that pattern and say if it matches that pattern, delete.
For some reason when I tried not P, it brought up something else and substituted it into the set.
Oh, really? Well.
For example, when I did not D, it input the date into the set. It sounds really.
All right, so there's a random file. So let's try this. So if we complement and we say print, and let's do a -n. So we'll only print things that don't match today. So we get those 3 lines. It might be something else that you had in there. And then the other option is, say, if you do match the pattern, delete, and I'm not doing a dash n, so it'll normally print every line except the ones that get deleted. So then you get those 3 lines also.
If you don't do the dash n when you're printing, why does it print everything twice?
Because without dash n, the default behavior is to read from the file and copy that to standard out. So every line gets printed at least once, but then additionally, if it doesn't begin with today, it also prints again because of the p command. So it's actually doubling every line except the ones that begin with today. Someone has an orange. It smells good. There's an orange. That's cool. Copy only lines that begin with today, well, that's just kind of the reverse, right? So, right, if we just say if it matches that pattern beginning with today, go ahead and print, right? And we could reverse the one that deletes also. So if it doesn't match a line beginning with today, go ahead and delete. What about removing blank lines?
What, is a blank line something that just starts and ends?
Mm-hmm.
So it's the beginning followed by the end.
Yeah. So we could just say if we match the regular expression $$, which means beginning of the line followed by the end of the line, that's a blank line. And if it matches that, go ahead and delete. Give it a file name. All right, so that gets rid of your empty lines. Of course, if there's spaces on these lines, it doesn't get rid of those. So how could you change your regex to deal with that?
It would have to identify any number of spaces.
So any number of spaces, including 0, so space followed by star. We'll match no spaces, which is a truly empty line, or any collection of spaces that makes the entire line. Bless you. So again, these are just examples, right? But the goal is to think about regular expressions, right? It's not that this is something that goes on your note sheet. It's just kind of practicing with these few building blocks, right? Particular pattern, repetitions of patterns, wildcards, anchors, to get better with regular expressions. All right, well, let's leave this, but play around with those. And there's usually some sort of sed and or awk question on the exam. So play around with these and ask questions. So let's shift gears. And let's talk about system programming and processes and things like this. So we know on a Unix system, right, we've got lots of things happening. If we do ps-elf, we can see every process that's running on the system. And there's a whole slew of processes. If we put it into word count, there's about 200 processes running. minus headers. And if you say top, you can see the ones that are taking the most CPU time. And if you just say PS, you see the processes associated with your terminal, which is generally your bash shell. And if you say PS, there's going to be a process for the PS command, right? And we know every time we do this, the process ID of the PS command changes. So 19927, if I do this again, it's 19928. The PID of bash itself is stable, right? Because bash is still running. But apparently, inside the bash shell, which is where I'm sitting right now, if I say PS, a new process is created, and that process is executing the command PS, right, which is this executable program under /bin, and other things happen along the way, but this process executes and it runs and then it dies. So we want to talk about how this happens, how processes get created. And a lot of you have already discovered one way to do this. And I don't remember what's needed for any of these things anymore. I was getting all kinds of compile warnings last night, so I'm just including everything right now. But there's a command called system. And it's used to execute a shell command, so it comes from standard lib. And it takes a string, which is a command, and it basically executes that command for you. And it's got some details here in the description that we're not going to worry about for now. But the basic punchline is just this, right? So we call system, we pass it a string, which is a command. It'll return an integer. We're not going to really worry too much about that integer. So let's just say system date. Actually, let's go ahead and let's save that. See what it returns. So this should run the date command for us. Right? So executing the date command runs, and then it says done executing the date command, and it says status equals 0. And some of you have used this to clear the screen in your programming assignments. You call system clear, and it erases the screen and stuff like that. Or you can call cause or whatever. Let's try that. Right, so nothing too startling. If we call a sleep command, it says executing the date command, and our program is stopped there while the command is executing. And then when the command finishes, it went on to our printf statement, right? So apparently this is some kind of synchronized or blocking call, right? And we won't continue with our execution until that finishes. And if we have a problem, then we'll get back a non-zero status, right? So we got an error because the command wasn't found. And the return status was 32.512, whatever the heck that is. So what is 32.5.12?
Random.
Non-zero?
It's non-zero. It's not random, actually.
Is it a specific error?
Partially. Right, so if I just execute zzz sleep from the command line, and I look for my status return, I get 127. But when I use the sleep command, I got status 32.5.12. Gotta find my BC command, there we go. But 32.5.12 is 127 times 256. Which I confess I knew ahead of time. So the return from the system command is actually 16 bits. And this is your error code from the command you're executing. And this lower byte, I believe, is the error code from the system command. It is telling you that the system command itself was successful, but the thing you were trying to execute had an error code of 127. So punchline, it's non-zero, something went wrong, right? But if you break it into two 8-bit chunks, right, this will usually be a 0, this will be the error code. So if you take your error code and just shift it right 8 spots, you'll get the return status from the error. Let's see if this works. All right, so I executed the command exit 7. And when we ran this, it came back and system had a status of 1792. All right, which is 7 times 256. All right, so system is useful. It's a nice way to sort of quick and dirty run a command. You can get some basic information back, but it's very hard to interact with that command. Right? If it's just something that's going to go off and do its thing and then it exits, and that's fine, like the date command, right? That works well. But if it's a system command that you want to interact with, for example, you want to use the BC command to do some calculations, right? The system just kind of throws it off into the background, and you don't really get a chance to work with it. So if I try to run user bin BC, it's executing BC, and BC is actually reading from standard in. So I can type in commands here, and then when I control D to exit that command, system finishes, it returns, and my program continues running. Right, so I can run a command that needs interaction with the user, and it will temporarily take over standard in and standard out. Let me type things in, it'll send output, and when that command exits, then we go back into the program. But it would be really cool if we could actually run a program from C and send some information to it and get some information back from it while the program is running. Right? Because then we could use a C program to actually tap into things like sed and awk and bash and BC and everything else, and actually take all the power of a Unix environment and use it as callable functions inside our C code. And we could do things like build a Linux system, by the way. So the next level of this is something called popen. So popen and close, right? Pipe a stream to or from a process. This lets us do something like an fopen. Okay, fopen opens a file. right? And we can write to the file or we can read from the file. popen basically opens something like this, or this. So if we say popen command for writing, it's basically opening not a file, but it starts running this command as a process, and standard in of that command is associated with whatever file pointer this popen returns. And we can write into this file pointer and inject things into this command standard input, right, from our C program, because it's just a file point. And if we do popen command for reading, then this command gets executed and its standard output is sent to whatever our file pointer is that we got back from popen. So we can run a command in the background and we can read its output through this file pointer. So let's just play with this. So I'll make a file pointer. I'll make a temporary string array. I'm going to execute the BC command. And I'm going to say let's write into it.
popen does not spell right.
How's that? Thank you. All right, so we're going to open up this command. We're going to say we want to write to it. And let's just take a look at what FP is. And hopefully it's not null. So let's send some things into our BC command. All right, so test code, right? So we'll do the popen, we'll look at FP to see what its value is, we'll send 3 things into the pipe, and hopefully BC will execute those things, and then we'll wait for the user here to hit enter, and then when they do, we'll do an F close on the pipe, and that should shut everything down. Expected that because FP is actually a pointer, but I'm not going to worry about it. So let's go ahead and run this. So executing the BC command, and so FP is equal to some non-zero value. That's good. Hit enter to finish. We didn't actually see anything display though. So let me throw this in the background and let's do a PS. Well, if I do a PS, I see that BC is running. Right, and I also see that SH is running and code 2 is running. So if I do PS-L, here's my bash shell. Okay, it's process ID 19778. That's the parent process of code 2, which I just executed when I said code 2, that had ID 2144. 2142 is the parent process of another process called sh. That's the default shell. That's the Bourne shell. It's like bash. And that's ID 145, and 145 is the parent process of this other process called BC. That's what's running through the pipe. That's 146. And here's the PS that I just executed, and the parent of that is bash. So BC is running, but it didn't display anything, right? We printed out the file pointer, and it said hit enter to finish. So let me go ahead and hit enter to finish. And it said closing the pipe, and now I got all of the output that BC generated. So stuff is kind of like asynchronous here, right? It's doing what we wanted, but kind of in its own way. And it's partially because everything is still buffered, right? So output doesn't usually occur right away. But it's not bad. So if we try to run this with a bad command, right? Our file pointer is still non-null, but we got an error from the popen command saying that that command's not found. But let's take a look at the PS again, right? So code 2 is 167. That's the parent of sh2 of sh, right? And sh was running this command, and that command didn't exist, and it's actually sh that gave us the error. So when you say system, it's actually not just executing your command, it's actually executing a shell, and that shell is being given your command. And the status on this shell has this funny thing next to it which says defunct. So that shell has basically been scheduled for termination, and it won't terminate until we actually exit code 2, but it's effectively gone. And these states are sometimes mysterious. There's actually a zombie state where you have a process that dies but it won't go away, and under state it'll actually show up as a Z, right? So it's a zombie. It's dead, but it's still there doing something, right? So zombie basically. Now if we go ahead and we exit this, it closes the pipe, and then all of that is gone.
What's FG again?
Oh, so FGBG, foreground, background. So you can run a command like this. If you hit Control-Z, it stops it, right? And it's no longer making progress. It's frozen, right? If you want it to continue running, but you still want control of the terminal, you can say BG, which puts it in the background, and now it's continuing to make progress. If you say FG, it'll bring it into the foreground, and now it's as if I had just typed the command. So anything I type here is being ignored because I'm running the command sleep 100. If I Control-Z it, anything I type is being picked up by the shell. So you've got your shell, reads from your keyboard, generates to the display, right? And when you type in a command, that command is now reading from the keyboard, sending to the display instead of the shell. If you put it in the background, it's running off on the side, and you're back in control of the shell. And FG just brings it back to where it was before you put it in the background. And Control-C just kills. All right, so before we talk about the next piece of this, which is forks, we want to talk about I/O. So fgets, right, is the command we normally use for reading from a file, right, either standard in or something that we've opened up with fopen. And in the top it says fgetc parentheses 3, right? So this is from Unix manual page chapter 3. which is sort of the user level commands, the stuff you normally call from a C program, say. So printf is in section 3, and scanf is in section 3, and so on. Section 2 is sort of the system level routines, the routines we don't normally call on a regular basis, but they're still callable from C. They're the things that are used to build things like printf and fgets and scanf and stuff like that. Right? So there's a hierarchy. There's user program, and the user program calls printf and fgets and things like that. And those call things like read and write and IOCTL, these lower level routines. And those routines make direct calls to the operating system. They basically generate interrupts, right? And the lower you go in that, the closer you are to the hardware, and the more rigid the interaction. When you get down to the level of calling an interrupt, you got to have everything lined up just right, because you're basically jumping into privileged operating system code. And if it doesn't like exactly what it sees, it's going to kick your request back to you. Level 3, printf, scanf, very forgiving, right? You can do pretty much anything you want. Very hard to cause trouble. So I want to look at these section 2 routines for doing input and output, and I want to look at read and write. And read and write are for doing basically binary I/O, right? Fgets, what does it do? It reads characters. If you get to a new line, it returns your buffer to you. If you get past the end of your buffer, it fills it up, it throws a null terminator, right? It's very sort of user-friendly. Read just pulls in bytes from an input source, right? And throws them into a buffer. You tell it how many bytes to read, give it a pointer to the buffer, and it doesn't care if there's new lines, it doesn't care if there's null terminators, it's just reading bytes, just binary data, right? And write is the flip side of that. You give it a pointer to a bunch of characters, tell it how many bytes to write, and a file descriptor, and it just starts sending these bytes out. Null terminators, new lines, unprintable characters, doesn't matter, right? So this is the low-level I/O routines. And you start this with open instead of fopen. So fopen is a buffered file descriptor. Open just returns an int. Give it a path name and some flags that tell it how to open the file, and it gives you this file descriptor. So here's some sample code. I have my temporary character array called buffer. I say open this thing called new file, and my flag is O_read only, so I'm opening this file for input. And it returns an integer fd, and I'm going to print out the value of that integer. And then I'm going to say read 10 bytes from that file descriptor, and I'm going to return the status from the read instruction. And then I'm going to print out each of those 10 bytes in hex, right, one by one, and then I'm going to close the file descriptor. So this is just playing with these low-level commands. Where am I supposed to get these from? Uni Standard. Alright, this is my day to get rid of syntax errors. Alright, so let's go ahead and run this. So open return 3, that was the file descriptor. And read return 10. Right, so file descriptor comes from the open command. That was a 3. And then I called read. I said read 10 characters and put the return value in status and printed that out. And status was 10. And then here's the actual data that it read from the file. Okay, so what is this 3? Anytime that you run something, you have 3 file descriptors always available to you: standard in, standard out, standard error. Standard in is your keyboard, or a file if you redirect, or a command output if you're piping, and so on. And this is file descriptor 0. Standard out is where printf and such appears. That's file descriptor 1. Standard error is used when you want to generate error messages so that if you're redirecting standard out, your error messages don't go into a file. They still appear on your screen. This is file descriptor 2. So what's the next available file descriptor 3? That's what I got when I did my open call. If I do another open call, it'll have probably file descriptor 4 and so on. So these are just straight indexes into an array of file descriptors. And the return from my read instruction tells me how many bytes I successfully read. I asked for 10 bytes. It actually read 10 bytes. So the read call returned a 10. And here's the actual bytes that it read. So these bytes are 4A, 4D, 5A. The next thing doesn't look like a byte. It looks like much more than 8 bits. So what is the deal with all these Fs? What does this look like in binary?
Very long series of ones.
Very long series of ones. So this hex number FFFFFF90, each of those Fs is a bunch of ones, and there's a 9, and there's a 0. And this first number that it read, 4D, is actually a bunch of zeros followed by 4D. So this is just kind of an artifact of the way that we do negative numbers in binary. Remember 2's complement, 250? All right. So when we try to print a number in hex, right, I'm printing with %x. I'm asking for 2 digits ideally. It looks at the most significant bit, right? And if that's a 0, it assumes this number is positive and it pads it with zeros to the left, and when we print it, we just get 4D. But if that most significant bit is a 1, that's a negative number in 2's complement. And if we were to try to print it as a 32-bit number, we would want to pad it with 1s. And so when we print it in hex, we get all those Fs in the beginning. So it's a bit of a red herring, right? This byte is really just 90, 0, 0, 0, 3, and so on. Okay, but it looks funny. And a lot of times when you play around with this stuff in the binary level, you'll see lots of Fs or 1s floating around, right?
Is it negative 90 or 90?
It's positive 90, but that's also negative something, right? And we could tell it that it was an unsigned int or something like that and probably get it to not do that. But the real answer is, it's this. Right? It's not really positive or negative, it's just a pattern of 8 bits. But printf with a %x wants to print it as a positive or a negative.
Because that's what you told it you want.
Because that's what I told it I want. So if we look at new file, let's look at it in hex. All right, so OD will show us the contents of a file in whatever format we want. So it shows us 5A, 4D, 0090, 0003, and so on. Well, that looks a lot like what we had up here. So now we can actually confirm 4D is the first byte of our file. That's what's being shown right here. And the second byte is 5A, that's what's being shown here. And there's our 90, and that's right here, and the fourth byte is 00, and that's up here, and so on. Now if you do this on a different system, you may see a different order. You may actually see 4D, 5A, 9000, 0300. Right? That can vary from machine to machine. But on this machine, the first byte is the least significant bits, the second byte is in the most significant bits. And this gets into something called the endianness. This is another 250 thing, big endian versus little endian. If you have an integer, that's, no?
No.
So, or maybe 270, or maybe not. So suppose we have the number 2,560 in decimal. Okay. So if we were to write this in binary, so this is A0. No, it's not. I'm lying to you. I'm not going to break out my hex calculator, though. Let's do the number 260, which is 256 plus 4. Okay, so that's what 260 looks like in binary. So we want to store this number 260. It's a 16-bit integer. We want to store that in memory. And let's say we want to store it at location 100. So there's two possibilities. Right, we've got 2 bytes we have to store. We could choose to store in this order, or we could choose to store in the opposite order. But your memory is fundamentally byte oriented, right? So we've got 2 bytes we have to store associated with this variable, I. And the address of I is, say, 100, so we're going to store it starting at this location. Do we store the least significant bit followed by the most significant? Or do we store the most significant followed by the least significant? And it varies from machine to machine. So that's called the endianness. And I got at least a 50% chance of getting it wrong if I tell you which is big endian and which is little endian, so I'm not going to. But one of these is called big endian, one of them is called little endian. And I've promised myself I'm never going to memorize those. So some machines are big endian, some are little endian. And normally it doesn't matter to you. If you're writing a C program, it does not matter to you. But if you're writing an assembly language program, it starts to matter. And if you're transferring information from one machine to another, it definitely matters. Because if I store this number on my machine, right, and this is the way that it's stored, and I transfer this file to another machine and I read it, but this other machine is organized with this endianness, right, it's going to think that the least significant byte is a 1 and the most significant byte is a 4. And this is going to be the number 4 times 256 plus 1, which is 1,025 instead of 260. And suddenly my data is like totally wacky, right? And when you've got networks and all your machines are connected and you can transfer images or data files or whatever from one machine to another, right, this becomes a frequent issue. So internet protocols have ways of specifying and adjusting endianness as well. So anyway, that's a tap into what's going on there, which we don't usually have to worry about, right? And even when we start doing networking, we're going to be going to and from the same machine, so this won't come up for us. All right, so we can do low-level reads, we can also do low-level writes, and we're going to use these as we move forward with this to start interacting with processes. We got 5 minutes. Let's start talking about where processes come from. So there's a function called fork. Okay, it's a section 2 function, so it's fairly low level. So disclaimer up front, be really careful playing around with calls to fork. Okay, be really, really careful playing around with calls to fork on the Linux server. chances are you won't get into too much trouble because I've tried to set things up with process limits and so on, but you can easily hose your machine by playing around with forks. Okay, so a fork bomb is like a really, really basic school kids attack on a Linux system. It's a way to fill up all the process spaces. And it takes no effort at all to make a fork bomb. And if you want to try this on your own system, it's fun to watch your system sort of melt down and then you reboot it, and it's usually okay. But if you happen to fork bomb the Linux server and the server goes down while people are in the middle of editing code and stuff like that, you won't make friends. Okay. So what is a fork all about? So return value equals fork. Well, it doesn't do much by itself. Doesn't seem to do anything, right? But let's do this. Let's print out the return value from our call to fork and see what it is. I'm going to open this up in a separate window because it's just that special. All right, you ready for this?
It's going to blow up.
It's not going to blow up, hopefully. What do you think the return value is going to be?
A lot. Numbers.
So what the heck happened here?
2 return.
We got 2 returns. One was 0 and one was something. 20466, which is pretty close to the process ID of this PS command I just executed. And if I run code 3 again, one of them was 0 and one of them was non-zero. So fork does something really peculiar. Fork makes a clone of the current process. And it's an exact copy of the code, of the memory, of the values of all the variables, exact copy of the original process with one difference, which is the return value from the call to fork. One process will get a return value of 0, the other process will get a return value that's not 0. Other than that, we got 2 identical processes now. So we'll sneak up to a fork bomb here. All right, so we'll just call fork 4 times and we'll print out the value that we get back from fork in each of those cases. And we get a bunch of stuff. And what's basically happening here is that when we make this first call to fork, we have 2 identical processes, which means each of those processes is going to execute the second call to fork. And then each of those processes that are created are going to execute this third call to fork.
It starts executing clones of the clones.
It starts executing clones of the clones.
And that's how you can get a fork bomb.
That's how you can get a fork bomb. So here's everything that executed. Right, so all of these. So if you were to make just sort of a while 1 equals 1 fork, right, that's a fork bomb. And it will very quickly do one of two things. It will either tell you that you have exceeded the number of processes you're allowed to open, and it'll just keep trying and failing, or it will actually consume all the space available for making new processes, and the system will crash. So on mine, I think it'll crash the system. So I'm not going to do that. But like I say, if you have your own system and you want to play around with this, save your work, go ahead and try it. All right, so we're going to start playing with fork tomorrow, and we'll build from there.